Welcome to AP Precalculus. Today, we're diving into the world of exponential functions and how they are used to model real-world data. The topics we'll be covering are exponential function, context, and data modeling. By the end of this lesson, you will be able to construct and apply exponential models to various situations. This is a powerful tool you'll use throughout your STEM journey. We have two main learning objectives today. First, you will learn to construct exponential models. This means you'll be able to create an exponential equation given certain information. Second, you will learn to apply these models. This involves using the equations to make predictions and interpret their real-world meaning. Let's get started. So, how do we spot an exponential pattern in data? The key is to look at the ratios of successive outputs. Unlike linear functions, which have a common difference, exponential functions have a common ratio over equal length input intervals. This means you multiply by the same number repeatedly. Let's look at an example. Imagine a cell population that grows as follows. At time 0, we have 5 cells. After 1 hour, we have 10. After 2 hours, 20. And after 3 hours, 40. To check for exponential growth, we calculate the ratios between consecutive outputs. The ratio of 10 to 5 is 2. The ratio of 20 to 10 is 2. And the ratio of 40 to 20 is also 2. Because this ratio, or growth factor, is constant, we know the data can be modeled by an exponential function. The growth factor, which we call b, is 2. Now, let's look at the structure of the exponential model. The standard form is y equals a times b to the power of x. Here, a represents the initial value, which is the output when the input x is 0. In our example, a is 5. The base b is the growth factor, or the common ratio we just found. In our case, b is 2, so our model is y equals 5 times 2 to the power of x. So, to recap, if you see a common ratio between successive outputs, you know you're dealing with an exponential relationship. The initial value is the output at time 0, and the growth factor is that common ratio. Sometimes, you might not be given the initial value or a table of data to find the ratio. What if you're just given 2 points? In this situation, you can construct an exponential model by setting up and solving a system of equations. Our goal is to find both A and B. Let's say a population starts with 10,000 bacteria, and after 3 hours, the population has grown to 50,000. We have 2 points, 0, 1, 0, 0, 0, 0, and 3, 5, 0, 0, 0, 0. This first point is actually a gift. Since x is 0, we automatically know the initial value A. Plugging x equals sign 0 and y equals sign 10,000 into our equation, we get 1, 0, 0, 0, 0 equals a times b to the power of 0. Remember that anything to the power of 0 is 1. So a is 1, 0, 0, 0, 0. Now we can use the second point, 3, 5, 0, 0, 0, to find b. We plug in 3 for x, 5, 0, 0, 0, 0 for y, and our newly found a equals sign 10,000 into the equation. This gives us 5, 0, 0, 0, 0, 0 times b cubed. To solve for b, we first divide both sides by 1, 0, 0, 0, 0, giving us 5 equals b cubed. Then, we take the cube root of both sides. The cube root of 5 is approximately 1.71, so b is about 1.71. Putting it all together, our exponential model for the bacteria growth is p of t equals 1, 0, 0, 0, 0 times 1.71 to the power of t. So, if one of your points has an x value of 0, the process is straightforward. If it doesn't, you would set up 2 separate equations and divide one by the other to eliminate a. We've now seen how to build an exponential model from 2 data points. Let's move on to our second objective, applying these models. A key part of this is understanding the growth factor, b. The base b in f of x equals a times b to the x is not just a growth factor, it also tells us the percent change per unit of x. We can calculate the percent change using a simple formula. Percent change equals the quantity b minus 1 multiplied by 100%. Let's apply this to our bacteria example from before. We found the growth factor b to be approximately 1.71. The percent change is 1.71 minus 1, which is 0.71. Multiplying by 100%, we get 71%. This means the bacteria population is growing at a rate of 71% per hour. That's a significant rate of increase. It's important to be able to go in the other direction as well. For example, if a car's value depreciates at a rate of 12% per year, what is the growth factor B? First, we recognize that a 12% decrease means the percent change is negative 12. We set up our equation, negative 12 equals B minus 1 times 100. Dividing by 100 gives us negative 0.12 equals B minus 1. Adding 1 to both sides, we find B is 0.88. A growth factor between 0 and 1 indicates decay or depreciation, which makes perfect sense for the car. So, to apply exponential models correctly, you must be able to calculate and interpret the percent change from the growth factor. Exponential models can be written in different but equivalent forms. These forms don't change the underlying function, but they reveal different information at a glance. Let's take a look at the classic compound interest formula. A equals P times 1 plus R over N, all to the power of N times T. This formula calculates the final amount A of an investment with initial principal P at an annual interest rate R, compounded N times per year for T, years. Let's work through an example. Suppose you invest $1,000 at an annual interest rate of 4%, compounded annually for 5 years. Here, P is 1,000, R is 0.04, and N is 1 for annually. Plugging these values in, we get A equals 1,000 times 1.04 to the power of 5. This simplifies to approximately $16.65. The 1.04 shows our annual growth factor. Now, what if we invested the same $1,000 at 4% interest, but this time compounded quarterly? Since it's compounded quarterly, N is 4. The formula becomes A equals 1,000 times 1 plus 0.04 over 4, all to the power of 4 times 5. Notice the difference. The term inside the parenthesis is now 1.01, representing the growth factor per quarter, and the exponent is 20, representing the 20 compounding periods over 5 years. Compounding more frequently gives you a slightly higher final amount. So, we've seen how a single model can be interpreted differently based on its form, revealing quarterly growth instead of annual. Exponential models are incredibly useful for making predictions, but it's vital to remember a key point. Context matters. Exponential models predict values within contextual domain restrictions. This means we can't just plug in any number for x. For instance, let's go back to our bacteria population, modeled by P of t equals 10000 times 1.71 to the t. Here, t represents time in hours. Is it reasonable to ask what the population was at negative 100 hours? While the equation would give a value, p of minus 100, the result would be a tiny fraction. Biologically, we can't have negative cells. And how accurate is this model extrapolating so far into the past, long before we even started observing the population? The model's domain is realistically for t greater than or equal to 0. The same goes for predicting the far future. What about the population at 1,000 hours? P of 1,000 would be an astronomically large number. In the real world, factors like limited space and resources would slow or stop the growth long before it reached that size. A simple exponential model doesn't account for these limiting factors. Another important concept is the natural base, e. The number e is a special constant, approximately 2.718. It naturally arises in processes of continuous growth and decay, such as continuous compounding of interest, radioactive decay, and population growth in ideal conditions. The formula for continuous growth is A equals P times e to the power of R times t. Here, R is the continuous growth rate. You'll use this form frequently in higher-level science and math courses. So, remember to always consider the context. The model is a simplification, and its predictions are most accurate within a reasonable domain. The natural base E provides a powerful way to model continuous change. Let's quickly recap what we've learned today. First, we learned how to construct exponential models. We saw that you can identify an exponential relationship by finding a common ratio between successive outputs. We learned that the standard form is y equals a times b to the x, where a is the initial value and b is the growth factor. We also learned how to find a and b by solving a system of equations derived from two given points. Second, we learned how to apply these models. We saw that the growth factor b tells us the percent change per period. The formula for percent change is b minus 1 times 100%. This allows us to interpret what the math means in a real-world scenario. We also saw how different but equivalent forms of an exponential model can reveal different interpretations, like the difference between annual and quarterly growth. Finally, we discussed the importance of contextual domain restrictions. A model's predictions are only valid within a reasonable range of inputs, and we introduced the natural base e for modeling continuous growth. Understanding exponential functions and their applications is a fundamental skill in precalculus. You are now better equipped to construct and apply these powerful models. Thank you for watching.